Okay, so let's continue on with the next part. So this is part 2. So we've already seen how to separate salt and water, and if you don't need the water, that's fine, you're just left with the salt at the bottom. But what happens if you need to keep the water? Well, this is a little bit more complicated of an experiment. So let's again do this. How do we capture this? Well, you might see something like this happening at home. If you're at home and you boil up a kettle. So again, here is my very bad kettle. But what will happen at home is when you boil a kettle, if you have it underneath, say, a cupboard or a kitchen press or something, as the steam comes out of the kettle, what you'll find is the steam hits the underside of the press or the cupboard. And when it hits it, it's cold under the underside of the press. And this is a gas, the water vapor. And what you'll find is when it hits the cold of the underside of the press, it cools the gas down. And when a gas cools down, it turns back into its solid version. Oops, sorry, not solid. Getting a bit ahead of myself there. It turns into its liquid version. So as a gas, it's steam. And as a liquid, it's just standard water. It's technically water in all variations, but we call them different things. Now again, that's okay, but we don't want it to hit the underside of the press, and then what do? Do we try and catch it in a cup or something? There's got to be a better method, and there is. So let's have a look at what the better method is. So we have to use a thing called distillation. And again, this is an experiment we would have been doing in the lab. And it's a video that I'm going to send on to you later this week when you have a good grasp of what's going on here. So here's the basic setup. What we have is we have something to hold our water and salt. And whatever it is in the lab, you know, it's funny glassware, but the glassware makes no difference. What matters is what's happening. So I'm going to put my salt in here. And again, this doesn't have to be a saturated solution. Here's my salt. And I've got my water. And I'm going to put a heating plate underneath it, or a hob or something like that. And we're going to heat that up to over 100 degrees Celsius. So basically what happens is the water is going to evaporate off. Now we need to catch this water. So in the lab in school, we've got some equipment that does this. So basically what we do is we put a stopper on the top of this, and we have a tube that goes up, and the tube goes down here. And I'll try and draw this as best I can. And this is a special piece of equipment. So we have a tube that comes straight out of here, and the water vapor travels all the way up the tube. Now this is just continuous water vapor. We don't want to collect the water vapor, we want to collect the water. So this special tube actually has a piece surrounding it, like this. And this piece of equipment is called a Liebig, L-I-E-B-I-G condenser. I'll explain why it's called that in a second. Now this Liebig condenser is connected to taps. So what we've got is we've a tap here, oops, and a tap here. And I think I've actually just drawn those around the wrong way. I want to tidy them up a little bit. And what happens is when we connect this to the tap, so this is tap in, we just put a hose on the end of this and we fill this with water. All of this in here is filled with water. And you can't draw it on this screen. You'll have to see a picture of it, even if you look it up on YouTube. This Liebig condenser completely surrounds the tube with cold water. So that means this tube here is cold, really cold. So what happens is, as the water vapor comes down here, oh, by the way, I meant to say to you, that is also a tap out. So you have a constant flow of water in the bottom. It fills this thing here, not the tube. This tube is sealed in the middle. Tube in the middle is sealed, and then you've got water flowing at the far side. Now, as the steam comes down, the steam hits the Liebig condenser, and because it's cold, the steam then condenses or turns back into liquid water. So you end up getting droplets of water rather than a gas. And the droplets of water then fall out the bottom. And then of course you can collect that. You can collect that in some sort of a jar or whatever. So that's the idea behind a Liebig condenser. And we use this distillation method to try and separate two substances where they're dissolved in each other, one's dissolved in another, but you want to keep the two substances. When you do this experiment, at the end of this experiment, you'll find that you have your round bottom flask and all the water is gone. And all you're left with is salt at the bottom of your round bottom flask, and you will have a beaker on the other side, whoops, and the beaker will be full of water. Okay. Another place we can use this, which you'll see in the book, is if we want to separate alcohol and water. So this is the last experiment we'll look at, how to separate alcohol and water. So exactly the same setup. The only difference is here is you have to understand a little bit more about the alcohol. So in this particular example, what happens when you have in here water and alcohol? Surely when you heat this, when you heat it up, it's going to boil off to two things. Well, it doesn't, because most substances have different boiling points. Now, most of us know that water boils at 100 degrees Celsius. So if you pop a thermometer into water, it boils at 100 degrees. So this is what's called a boiling point. And we know that, but you've got to know what boiling point means. Boiling point means it changes state. And that means it goes from a liquid to a gas. But it only does that at bigger than 100 degrees Celsius. Alcohol also has a boiling point, but alcohol's boiling point is 78 degrees Celsius. And we'll just write BP for boiling point. Now, what does that mean? Well, that means if I turn this dial, this temperature dial, to say 85 degrees Celsius, what's going to happen is, let's say the alcohol is there in red. What's going to happen, even though the two things are mixed, because it's at 85 degrees Celsius, the alcohol is going to boil because it's greater than its boiling point. And the alcohol boils off. Why? Because it's only got a boiling point of 78. This here is your alcohol vapor or gas. It's the same word, alcohol vapor, alcohol gas. And that's going to escape. The water won't go anywhere because you have not, at 85 degrees Celsius, you haven't hit water's boiling point, so it stays as a liquid. After this, the alcohol vapor travels up and we use a Liebig condenser to catch the alcohol. So instead of water passing all the way through, it would be alcohol passing all the way through this time. And again, the alcohol would dribble out the bottom and we would collect it. So there's another example of how you would separate two substances like alcohol and water. You can also do this, by the way, with Coca-Cola. So if you take any Coke product, you can do the same thing. You put your Coke in here, and when you boil it, it will boil off the water. The water will boil off, H2O, and you will be left with Coke syrup at the bottom of the glassware. I don't recommend doing this because it sticks to the bottom of the glassware and you can never get it off. It's awful stuff. So that's how we separate substances where one substance is dissolved in another. Up here, again to revise, we separated sand and water where one substance is not dissolved in another. And we also looked at separating salt and water where we weren't too worried about keeping the water. We just wanted to boil off the water and be left with the salt. So that finishes up the experiments. Let's move on to one or two more small things and hopefully that'll help explain it a bit more. Give me 1 second, I'll be back to you. So here is a question from one of the worksheets that I actually sent you out, and it's to do with conductivity. So we're going to have a quick look at it. Conductivity is fairly easy to explain. So here's your definition here. A conductor is a material that allows electricity flow through it. And basically, as a rule, that's metals. So most metals will allow electricity to flow through it. An insulator, which is the next one, so that's an insulator. This is a material that will not allow electricity to flow through it. Okay, so this is often non-metals. And again, what are non-metals? Non-metals are things like plastics, wood, that sort of stuff. In order to have a go at this question, you need to know what this diagram means. And this is from the electronics section. And again, this is something we would hook up in class if we were there. So a couple of things. So the first one is this one here. This is a bulb. So this is a light. Up here, this is a battery. So your standard AA battery. And the battery's got two terminals. So this side, the bigger side, is the positive terminal. And this side is the negative terminal, this little line here. This thing here on the left is a switch. And then these two things here this is where you are going to insert your material. So here's the basics of what happens. When you connect up the circuit, a circuit has got to have a full flow. Electricity flows from the negative end and it flows all the way around. It flows through the bulb, it flows into B, it flows into whatever you've put there, into A, around through the switch, and when you close the switch into an on position, so in other words, when you take this and push it down there, so when this is closed, it will also pass through here and back around to the positive end of the battery. And if it completes one complete loop all the way around without any breaks, then you have what's called a full circuit and the bulb will light. What this question is asking you is when you put your material in between A and B, will electricity be allowed to flow through it? So for example, if you put in an iron nail in here, will the electricity be able to flow all the way through the iron nail? If you put in another replacement, so if you put in wood or if you put in plastic, will it be able to pass through? And that's your investigation into conductivity. 2 videos were helpful. It is hitting around 11:30 here, so I'm going to go to bed. But if there's something else that you need or something you don't understand, please message me on Google Classroom. I'm going to, using this software that I've got here, I'm hopefully going to answer all the questions on the worksheets that I've given you and send them back to you so you can correct them yourselves over the next couple of days. So best of luck, use the internet, use your books and try your best. And if you don't get it, don't worry about it. We'll be going through all this again whenever we return to school. Okay folks, take care, mind yourselves, bye.